yes. Dressing up y equals x squared, we're going to investigate the effects of three types of transformations on the basic quadratic y equals x squared. First one involves multiplying by a number, so 2x squared negative 5x squared 0.5. The second involves adding or subtracting a constant to the variable x, so x plus 4, then we square, or x minus 7, then we square. And the third involves adding or subtracting a constant to the x squared term, right? So x squared, then add 6, right? Not add a number and then square, but square and then add a number, or subtract. We will then examine the combined effects of all three transformations together. So some examples are y equals 2, bracket x minus 3, bracket squared minus 6, and y equals negative 3, x plus 5, quantity squared, plus 2. So I'm going to say this out loud. I'll say like x plus 5 quantity squared, which implies that you have to do the x plus 5 first. In general, we'll investigate the effects of a, p, and q on the quadratic function in the form y equals a, x minus p, quantity squared plus q. To do any of this, we got to start off with just the basic x squared function. So we want to be very familiar with what that looks like. We're going to complete the following table. We're going to use those points. We're going to graph this, and we're going to sketch a graph. When I say sketch a graph, or we say sketch a graph on any quiz, test, whatever, I want to see accurate points, and then, I want to see it drawn correctly, which is not joining the points with straight lines, but with a smooth curve. But if it's not exactly to the points, much can be forgiven, but the points need to be in the right place. Okay, so we're just going to square the x's. And then we're going to graph this. So we have negative 3, 9. Oh, let's use a different color. Let's get the lead out, get the red out. We have negative 2, 4. We have negative 1, 1. We have 0, 0. 1, 1, 2, 4, 3, 9. And we join those, and then what do? We draw an arrow to indicate that this keeps going forever. And there's your basic y equals x squared, right? And then what we want to investigate is, so what's going to happen to this when we multiply it by a number? Or when we add or subtract a number from the x before we square. Or when we add or subtract a number after we square. Okay, but this is always our starting point, right? We're always going to start there. Then we do stuff. What's the name of the shape? It's a parabola. What are the coordinates of the vertex? These are coordinates. It's an ordered pair. It's in parentheses with a comma in between, right? What is the equation of the axis of symmetry? X equals 0. All right, we good? First page, left-hand side, really. Moving on. Use a graphing technology to do the following investigations. The effects of y equals ax squared. On the same set of axes, sketch the graph y equals x squared, where a is a half, 2, 3, negative 1, negative 2. Copy the graphs onto the grid to the right using a different color for each graph. Label each graph with its equation. The graph y equals x squared is shown. Okay, I'm going to do this. I'm going to do this using Desmos because it'll show me everything and it'll graph nicely. And it'll label the equations nicely. But you can't do this on, on a test because you don't have access to that. So let's just start with y equals x squared. For spacious skies and amber waves of grain. All right, what else do we want? We want 1/2 x squared. We want 2x squared. We want 3x squared. We want y equals negative 1x squared. And we want y equals negative 2x squared. Okay, so there they are. All of them are there. Okay, we have different colors for each, which you can't actually see on this. So let me see if I can pick up the frame and move it a little. No, look at that.
It's recording, so you pull it.
There we go. Okay, so now we can see the different colors as well, right? So the colors match up with graph. You can do this at home, of course, right? On any device. You could do it on a tablet. I think you could do it on a phone, but that would be just kind of silly because that's just a really small display. So, but on a tablet or a desktop or a laptop, Desmo should run on anything out of a browser. So, let's answer some questions. So I'm not going to graph these onto the notebook file, right? I mean, it's just they're here, and now we can say stuff about them. So let's say stuff about them. Does changing the value of A change the position of the vertex? No. So the vertex did not change. Compare the three points on the graphs y equals x squared, y equals a half x squared, and y equals 3x squared with an x coordinate of 1. What do you notice about the y coordinates of each of these points?
They are special.
So when the x coordinate is 1, y equals x squared has a value of?
So it's not one.
Oh, sorry. When it's 1, y equals x squared has a value of? 1. Okay, so y equals x squared is the, I don't know, reddish. What else were you supposed to do? A half x squared? So 1/2 x squared, that's kind of purpley, I guess. So 1/2 x squared, we have a y value of 1/2. And what else were we looking for? 3x squared. And 3x squared is kind of, I don't know, looks black, kind of. So that would be here. And we have a y value of 3. Interesting. What do you notice about the y coordinates of each of these points?
They're the same as the coefficient.
Yeah, they're the same as the coefficient. Are the same as the leading coefficient. Also known as A. Same as A. Compare the 3 points on the graphs y equals x squared, 1/2 x squared, and 3x squared with an x coordinate of 2. Okay, so we want an x coordinate of 2, so we're taking y equals x squared, which is this guy, but we want an x coordinate of 2, and we get y coordinate of 4. That's what 2x, oh, sorry, where's that? We're supposed to do 1/2 x squared. So y equals x squared, all right, sorry. So y equals x squared was at 2. Y equals x, oh, yeah, 2, 4. And 1/2 x squared, which is what color? Kind of blue, I guess. So 1/2 x squared, what do we get?
Wait, what?
2. And what was the last one?
3x squared.
3x squared, which means we have to move the graph a little. And maybe zoom out a bit. Okay, so now 2 is here, and 3x squared gives us a value of 12. Okay, and so how does that compare to whatever it is we were comparing it to? What do you notice about the y coordinates of each of these points?
Compared to x squared, each of those are greater by a.
Compared to y equals x squared, each y coordinate
Is greater by.
is ax squared, right? You're going to multiply by the value of a. So 1/2 x squared gave us 2, right? Half of the y coordinate. So we had 2 4, we had 2, 2, and we had 2, 12, so that the y-coordinate was multiplied by 1/2 or multiplied by 3, depending on which one we were looking at. So in general, what effect does A have on the graph?
Depends on what
It's a vertical stretch by a factor of A. Let's clear this out. About the x-axis. So actually this is about the x-axis. So we would say vertical stretch about the x-axis by a factor of A. As the size of the absolute value of A increases, right, so the absolute value of A, as that size increases, then what's going on?
No, how the graph changes accordingly.
Wow.
Okay, we're done with this lesson, man. The graph's going to change for all of them. We could just use that in general. What happened? The graph changed. Okay, good.
Okay, good. Full mark.
Done. Yes.
If
Want
A is,
to be more specific, maybe, that's all.
if A is less than 1, then, well, if A
No. The size of the absolute value of A increases. Size of the absolute value increases. What happens?
A is less than 1, or if the absolute value of A is less than 1, then the graph will be it's fine. How to put it into words, yeah.
I think this is what you were trying to say, right? Yeah.
Yeah, that's what it's
Well, it changes though, just sort of.
It just changes.
Just write that down for every answer from this point on, and we're done the sheet. Okay, it changed, yeah. When didn't it change? Well, we didn't change anything, and then it stayed the same. Sorry.
When the factor was 1.
I don't know. It was just too good to pass up. When A is positive, which way does the parabola open?
Upward, downward.
Okay, so
Well,
A
not there yet.
positive,
Downward. When it's positive.
up, A negative, not to be confused with blood types, down.
Why do you make so many positives?
What if I'm at home?
How do graphs compare when the values of A are the same except for the sign?
There's 8
Okay, so how does negative, let's take off some of these like this and this. Okay, so we got y equals x squared. Let's compare y equals x squared to y equals negative x squared. How do these compare?
It's the same. Parabola way.
The same thing except it's like front.
The parabola opens a different way.
And how do these two compare?
The parabola.
Same stretch but different way.
So we will say they are congruent.
Exactly.
They are congruent. What does congruent mean? They're the same. The congruent are graphs. The graphs okay, so same shape, different direction of opening. The graphs of y equals x squared, 3x squared, 0.4x squared, and 5x squared, as well as the graphs of two other functions are shown. Label each one with its equation. So how are we going to tell them?
I have to find the coordinates.
What coordinates?
0,
0, 0. It's all the same. 0, 0. It's all the same to me.
Do x equals 1 and then c.
Right. Do x equals 1, and then y will equal the coefficient, right? Since 1 squared is 1. Or you could do negative 1. So if we take x as 1 or negative 1, squaring that gives us 1. Multiplying by a then gives us a. So looking along here, we should get the value of a. So this graph here, which is lowest, will be y is equal to 0.4x squared. This one is x squared. This one is. This one is. This one is.
I don't know. Too lazy. Negative 103.
It looks like it's congruent to this one, right?
But it's
And this one is.
the other one's 0.4.
Okay. So basically all we're doing is we're looking at when x is 1 or negative 1, since 1 or negative 1 squared is 1, then the y value will be equal to a, right? Because we got ax squared. This holds no matter where the vertex is, right? So here's how you do it. You just say, here's the vertex. I'm now going to move 1 unit to the left or to the right. However far up I go or down will be the value of a. If I'm going down, then a is negative. If I'm going up, a is positive. Okay? So you can identify the value of a simply by moving 1 unit from the vertex in either direction and then saying, okay, I should be going 1 unit, right? Should be 1, 1. If I go 2, it should be 2, 4. If it's 2 and less than 4 or greater than 4, then that will also be a, right? If it's some multiple of 4. You know, here it's like 1.6, but that's not really easy to see, right? I mean, if this were 2, then I'd say, oh, that's a half x squared then, right? Because it should have been 2, 4, but it was 2, 2. Should have been 3, 9, but it was 3, 4, and it's too easy to, right? So it should have been 4, 16, but it's 4, 8. Then that tells me my a value is a half. Okay. If it was a quarter, then it should have been 4, 16, but it was 4, 4. Okay. So you can tell by basing it on the stretch. Whoa, that was just like way too many pages. Okay, let's scroll and not use arrows. The effects of p on y equals x minus p quantity squared, right? So we're going to add or subtract a value to or from the x before we square. On the same set of graphs, graph y equals x squared and y equals x minus p squared, where p is positive 2, positive 3, and negative 4, which I, of course, will not do on those graphs, but I will do. So we're always going to start with y equals x squared, right? Because I want to see what the basic function looks like. And now we're going to graph y equals x minus 2 quantity squared. Let's just clear this off. And we'll go here. So y equals bracket x minus 2 bracket squared. Where did it go? It moved. Where did it move? To the right. How much?
By 2.
By the root.
So where's this one going to go?
To the 3. To the left. Oh, yeah. To the right.
Oh, yeah. To the right.
And if I do y equals x minus negative 4.
That's positive 4. It goes to left 4.
Yeah.
Then it goes to the left 4. So y equals x minus negative 4 squared really should be written as x plus 4. Okay? But then again, let's rewrite it as y equals bracket x minus negative 4 bracket squared. Okay, so we can see it in both forms, right? And realize that things are going places, right? Stuff's going places. Equation. So where is the vertex of y equals x squared?
0, 0.
0, 0. Where is the vertex of y equals x minus 2 quantity squared?
2 squared. 2 0.
2, 0. Just checking. 2, 0. Where is x minus 3 quantity squared?
3 0.
Where is x plus 4 squared? Negative 4, 0, right? Or this is x minus negative 4 squared, right? You should have noticed that all the parabolas are congruent, right? They're kind of the same size and shape. If p does not affect the shape and size of the graph, then what effect does p have on the graph?
Moves the vertex.
Which way?
The left
Depends on the
right.
side.
Okay, we're going to call that
The
horizontal. Yes, so we're going to call that a horizontal translation. So what does it do? Then what effect does p have on the graph? It moves the vertex. Left or right. Okay, we're going to call that a horizontal, just not the vertex, right? It moves the vertex and all other points. And all other points. Just the vertex is easy to see, right, where it went. It's not like, hey, the vertex moved, everything else stayed the same. That would be kind of silly. So every point moves the vertex and all other points left or right. It's a horizontal, so we're going to call it a horizontal translation. And how does it move? You know, like when I subtract 2, it moves to the right. And when I add 4, it moves. So it's kind of in the opposite direction, right? Okay, so horizontal translation moves opposite.
It looks like it moves by the root or then 0.
Yeah, it moves to 0, yeah.
No, it moves like the 0 of this. 2, right? So it moves in 2.
Like,
IB.
Yeah, like bracket x minus 2.
In order to get y to be 0 here, I have to put x as positive 2, right? That's how I'll get a y value of 0. So move the vertex 2 units to the right, or 4 units to the left. Okay, good. I don't care how you think about it. You just got to think it's backwards, right? That's how I always think about it. Complete the following statements. The graph of y equals x plus 5 quantity squared would be the graph of y equals x squared translated horizontally. 5 units to the left. The coordinates of the vertex y equals x plus 5 quantity squared are negative 5, 0, right? In brackets, or sorry, in parentheses with a comma in between, right? Because it's a point. The graph y equals x minus 7 quantity squared would be the graph y equals x squared translated.
7
Units to the right. The coordinates of the vertex are.
7, 0.
If p is a positive value, the equation will look like y equals x minus p. You're going to see a negative sign there, right? The graph of y equals x squared is translated horizontally. Describe the direction of the translation and how far the graph is translated.
Draw some right. Can we just write?
To the right, how much? So horizontal translation. So we're going to say what kind of translation? Because what other kind is there? There will be vertical translations, right? We're not there yet. We're going to get there in a moment. So we're going to say what kind of translation is a horizontal translation. We then need to say how much and which way, or which way and how much, depending upon how you feel. I don't really care. So it's a horizontal translation. P units, which way? Right? Okay? No. In 2A, it's right. Okay, so it's a horizontal translation, P units to the right, or you could say right P units. Okay? So you're going to state the following stuff for horizontal translation. You're going to say it's a horizontal translation, or you may use the abbreviation HT, right, for horizontal translation. Then you're going to say how much and which way, or which way and how much. So you could say HT P units right, or HT right P units. If P is a negative value, the equation, you'll see a plus in there, right? Because P is the value that follows a minus sign, and minus and negative gives you the plus. Graph y equals x squared is translated horizontally. Describe the translation, how far the graph is translated. HT left P units. Okay? So either way, right, you could say HT. You're always going to start off with what kind of translation? HT. And then you can say left or right. You could say which direction and then how much, or you could say how much and which way. Me, I prefer left or right first because it lets me know which way I'm going as opposed to the 5. Okay, 5 what, right? Well, okay, 5 units, right? Doesn't much matter. I can, assimilate that information either way it comes, but if you say you're going to move left 4 units, then I could start moving before, I'm going that way, right? I know which way I'm going. What are the coordinates of the vertex y equals x minus p quantity squared? P 0. Okay, so p is positive, then, right, it's the number that follows. X minus 5 squared is 5 units to the right, gives you 5, 0. X plus 5 squared, p would be negative 5, right? If it follows a plus sign, then the p value will be negative. Determine, really it's state, right? Because we're not really determining, we're just going to state the equation of each graph below. What is A?
X minus 1 squared.
Y equals x minus 1 quantity squared. What is B?
Y equals x plus 4 quantity squared.
X plus 4 quantity squared. And C?
Y equals negative x minus 1 quantity squared.
Okay, y equals negative because it opens down. X minus 4 because it's moved 4 units to the right. Right? Wow, let's just fly through this. Then you can actually have some time to study for your test tomorrow.
Which we're all going to fail.
Probably. Part D, the effects of Q on y equals x squared plus Q. First we square the x, then we add the Q. On the same set of axes, sketch graph y equals x squared plus Q, where it's 1, 3, and negative 4. So let me go to my set of axes and just clear these out. So always start with the first, right? Y equals x squared. Then we're going to go y equals x squared plus 1. Right? And then we're going to go, what's the other two? Plus 3. X squared plus 3. And then we're going to go y equals x squared and do what? Minus 4. I should have been a plus 3, right? Okay, minus 4. And plus 3. Oh, did I? Okay. I couldn't see it. Looked negative to me. Okay, so question is, what's happening here, right? You can see what's happening here. What's happening?
They all have the same axis symmetry, but their vertex is a bit different.
Okay, so axis symmetry, are the graphs congruent?
No.
Yes, they are.
Essentially,
Oh wait, no, they're not.
yes, they are.
Graphs congruent?
Sometimes.
It's just a vertical translation.
Yes.
Yes, they are, right? They're not going to look at it because, well, that looks like it's pulled in more, but yeah. They are congruent, right? If I slide this one down, so if I slide this down 2 units, and if I take this point here, which is at 5, and slide it down 2 units, oh, sorry, 1 unit, two ticky things, right? The 5, then it ends up there, so yeah. Okay, so they are congruent. Record the vertices. Y equals x squared. Vertex is 0, 0. 1 x squared plus 1? 0, 1. X squared plus 3? What? And lastly, are the graphs congruent?
Yes.
In general, what effect does Q have on the graph?
Vertical translation.
Vertical translation. Moving which way?
Up or down?
Okay, so up or down. Vertical has an AL, not an LE. It's not an icicle, it's a vertical. Complete the following statements. The graph of y equals x squared plus 5 would be the graph of y equals x squared translated.
5 units up.
5 units up. Or you may say up 5 units, right? But not in this case because blanks only fill in nicely. Coordinates to the vertex are 0, 5. The graph of y equals x squared minus 10 would be the graph of y equals x squared translated. 10 units. Which way? Down. Coordinates to the vertex are 0, negative 10. If q is a positive value, the equation will look like y equals x squared plus q. The graph of y equals x squared is translated vertically. Describe the direction of the translation and how far.
Goes up by Q.
VT, vertical translation, up q units, right? Or you could say q units up. So translations need what kind of translation, and then which way and how much, or how much and which way. Okay? Your choice. Don't care, right? Whatever works for you. If q is a negative value, the equation will look like y equals x squared minus q. The graph y equals x squared is translated vertically. Describe the direction of the translation and how far the graph is translated.
Down 2 units.
Right, I'm just doing one of each so that you can see I don't favor one over the other. Right. Please ensure that if you have receipts to submit, we get them on Monday. Go.
What?
I hiccup. What are the coordinates of the vertex y equals x squared plus q?
0q.
Okay, 0q. So in this case, it does what it says it's going to do. You say plus 5, it goes up. You say minus 10, it goes down. Right? Unlike a horizontal translation where things are backwards. You say plus, plus to me should be to the right, it's to the left. Determine the equation of each graph below. So what do we got? B. Okay. Now, are you sure it's not negative x squared minus 1? Did we make the whole thing negative? Now, this tells you it opens down. This tells you it moved up 1 unit, right? Up 1. And C. Okay. Party. Party. Oh, it's tomorrow, right? And we write the test. You write the test, I party.
Oh
I get
god.
to watch you like that.
Putting it all together. Yeah, that's right. Get to watch you sweat for a while. Yeah, I'd say something like show up on time, but show up on time. Yeah. And yeah, 'cause no extra time, right? Starts at 9, well, 8:50, whatever, ends at 10:25.
Why did it so bad?
Suppose you want to sketch the graph of y equals negative 2, x plus 3, quantity squared plus 4. How do you handle all 3 transformations? First, you have to determine the effect of each of the numbers. Describe the transformation the 2 made.
Changes the vertical graph.
So I'm going to describe it as about the x-axis, right? Which, you know, in a sense, we don't have to, but I'm setting you up for 30-1 when there's a whole pile of transformations in there, right? So if you're just used to saying vertical stretch about the x-axis by a factor of 2, or vertical stretch by a factor of 2 about the x-axis, right? Again, doesn't really matter what order, but you should say both, or at least understand we're stretching about the x-axis by a factor of 2. Describe the transformation the negative sign made. Yeah, how else? It's a reflection in the x-axis. Okay, it's a reflection in the x-axis. That's what makes it open down. describe the transformation the plus 3 made.
3 units to the left.
So HT left 3, right? A horizontal translation left 3 units. And the plus 4?
VT
Up 4, 4 up. Don't care, right? Just as long as both are there, right? So there must be a direction and there must be a quantity, right? So how much which way or which way how much doesn't matter. All right, flying through this, we will graph in 4 steps because, why do it when 1 would suffice? So this is the only one we're going to do this way, right? We're going to graph in 4 steps. So we're going to do each transformation one at a time, and then I'll show you how you can just do it all together.
Oh no.
Okay?
You think I care?
Oh, hey, we're almost done. So, first thing, we're going to plot the points of y equals x squared. Key points of y equals x squared, right? We always start with the basic quadratic, which is x squared. That's the basic quadratic, right? So we got 0, 0, 1, 1, 2, 4, 3, 9, and symmetrically the other side. Okay? So, plot the points first. Then you can join, right? We got key points. Plot the key points. Okay. Because really, it's the points we care about, right? I mean, the graph just follows because you just, you plot it on the points. Next, we sketch the graph of y equals 2x squared. The order actually matters, right? The order in which transformations are done matters. You start with, it's like getting up in the morning, right? It's the first thing you do. You get up in the morning, first thing you do is just stretch. Well, you stretch a little bit, right? Okay, watch your dog get up in the morning. Your dog is going to stretch. Okay, you should too. Do a little bit of stretch. Then you walk into the bathroom and you look in the mirror, so there's a reflection. Okay, and the translation part, then you come to school and you're in Spanish or French, whatever language, and you have to do some translations, right? So, stretches, followed by reflections, followed by translations. So, we are now going to graph y equals 2x squared. In order to do this, we multiply the y coordinate of each key point by 2. So the y coordinate of this point is 0. Times 2 is 0. Okay, let's just get through this quietly. The y coordinate of the point 1, 1 is 1, so it becomes 1, 2. The y coordinate of 2, 4 is 4, so it becomes 2, 8. And 3, 9 becomes 3, 18 off the scale, right? So negative 1 squared is 1 times 2 is 2, negative 2 squared, and so on. Okay, and now we can graph. This is now the graph y equals 2x squared. Okay, this is the graph y equals 2x squared. We now want to take that graph, right? We sketch the graph of y equals negative 2x squared. The effect of the negative sign is to reflect the graph of y equals 2x squared in the x-axis. So we're going to change the sign of the y coordinates, right? So 0, 0 becomes 0, 0, right? 1 was at 2, so it becomes negative 2. 2 was at 8, so it becomes negative 8. By symmetry, the same thing is happening on the other side. So now we have the graph y equals negative 2x squared. How do we know it's negative? It opens down, right? It tells me I've got a negative leading term. Lastly, to finally graph y equals negative 2x plus 3 quantity squared, we translate the graph of y equals 2x squared 3 units to the left and 4 units up. Okay, so we take each of these points and we go 3 units to the left and 4 units up. Okay, now I'm going to show you how I do it all in one step, which is if you graph the graph, then how do you get there in one step, right? Which is just because the final result's the final result. So here's what I do. I say, I know I have a point at 0, 0, right? I'm going to stretch that vertically by a factor of 2. Okay, it doesn't go anywhere. I'm going to reflect it, doesn't go anywhere. I'm now going to move it 3 units to the, which way are we going, left? 3 left and 4 up. So I take the point 0, 0, I do the stretch on it, and I do the reflection on it, and I move it 3 left and 4 up. So there's 0, 0. I'm now going to take the point 1, 1. I'm going to vertically stretch by a factor of 2. I'm going to reflect it. And now I'm going to move 1, 2, 3, 1, 2, 3, 4. And there it is. Okay. I'm now going to take the point 2, 4. This is on the original graph, right? I'm going to stretch it by a factor of 2. It's at 2, 8. I'm going to reflect it. It's at 2, negative 8. That's the one that's over there, right? And now I'm going to move 1, 2, 3, 1, 2, 3, 4. And there's that point. I'm now going to take the point negative 1, 1. Stretch it by a factor of 2, reflect it, go 1, 2, 3, 1, 2, 3, 4, and we're here. And I'm now going to take the point negative 2, positive 4, stretch, reflect, 1, 2, 3, translate, 1, 2, 3, 4, translate. And if we look at this red graph, it's really if I just took each of these points and did the whole left 3, up 4. But, you know, in real life, you're not going to do it in 3 separate steps, right? So what you need to do is you need to be able to look at negative 2, x minus 3 quantity squared plus 4. You need to be able to describe in words, and I cannot emphasize this enough because you're going to do a lot of this in grade 11. Okay, when you're doing 30-1, you need to be able to describe in words each of the transformations, right? And you need to do it by doing stretches first. So you look at that and you say it's vertically stretched by a factor of 2. Then you look for the reflection. You say and it's reflected in the x-axis. And then you look at the translations and say, and then it goes left 3, up 4. Okay? And then you can take the original graph, y equals x squared, and you just do all of that to it one step at a time, right? I'm going to stretch by a factor of 2. Then I'm going to reflect. Then I'm going to go left 3, up 4. Here's my new point. And I'm going to do that with each of the key points that I can. Right? I'm not going to bother with 3, 9. Right? As soon as I stretch, I go to 3, 18, say, yeah, okay, and then 3, negative 18. Okay, it's off the graph, right? So off the grid. You want to be off the grid, so you stay on the grid, and away you go. Okay, so if we then go on to look at practice, 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 which strikes me as stuff that you should be doing, then you're going to see that you have all of these different equations, and you have a number of different graphs, and you have to match them, right? So you can figure out by looking at that, well, hey, where's the vertex? Where's the vertex? Negative 8, 0. So and which way does it open? Opens up. Is there anything at negative 8, 0 opening up? Yeah, there's only one graph, right, that meets that criteria. This one is at
Negative 8, 0.
and opens down. Okay, so it's got its own letter, right? This one, now you look at these, right, and you could say, hey, each of these, okay, these two are the same and these two are the same. So we know with this one, it's
Negative 5, 4.
yeah, the vertex is at negative 5, 4. So you just look for a vertex of negative 5, 4, and there you go. And this one, it's at whatever. This one, you know, and this is stretched. So you expect to see something that's vertically stretched. And here they're vertically stretched. And a lot of these open up. Okay? So you can figure out where the vertex is, and you can figure out the direction of opening. And then you can match each with its appropriate one. Now, we move to here. Given the equation, you want description of transformations. This is key. Okay? This is key to 30-1, is being able to describe these transformations. Because you're going to spend the entire first unit describing transformations, right? And you're not just doing transformations on the quadratic. It's going to be transformations of everything. Okay? And I don't know if you have to transform conic equations, because that used to be in pure 30. May still be in IB, I'm not sure. If you do, then they'll learn you how to do it, right? But it's all the same. So here's the key thing to remember about the whole of transformations that you do in high school or ever. Nothing ever changes. There's no special cases, okay? There's no such thing as a special case. When you do something, it always does what it says it's going to do. When you have x plus 3, that will always move left 3. It's not like, oh, it's left 3 unless it's Wednesday at 2 o'clock, in which case then it becomes right 3 or it becomes down 3 or whatever, right? When you see the x minus 3, so when you learn transformations in 30-1, when they say this does this, it always does that, okay? There are no special cases. Okay, so you need to be able to look at this and you say, this is a vertical stretch. I'm not even going to look at that, right? It's a vertical stretch by a factor of 3 reflected in the x-axis. Horizontal translation, right? 4, vertical translation up 5. Okay, where's the vertex? Well, it was at 0, 0. Stretches and reflections will do nothing to the vertex, right? Because the vertex is on the line about which you are stretching and reflecting. So the vertex is invariant, does not vary under a stretch or a reflection. It can't go anywhere, right? You cannot stretch away from the line if you're on the line. You cannot reflect in the line if you're on the line. So the only thing that's going to move the vertex is this. So your vertex, all you're looking at is the P and the Q values, right? Okay, so you can do this. You got 27 people to check with, and then if you cannot get the answer, you have the 28th person to check with, right? I'm the 28th person. You check with me afterwards. Okay, and then we move on, and we have this. I don't know what that's for, but it must be for whatever's below. That's a... Were there instructions on it? Were they at the bottom of the last page or something?
It's at the top of the last page. We have to graph all these equations. They're at the top of the page.
Whatever. Really, bottom of the page before? Oh, for each of the following quadratic functions, describe the transformations, determine the coordinates of the vertex.
I've checked it.
Oh, you're supposed to graph them all, right? That's it. Okay. So, on this grid, they're giving you x squared. You're going to graph all of the preceding stuff, right? Okay? And then at the bottom of that page, you will then summarize everything, right? And that will about do it for dressing up y equals x squared. Okay, so you have